Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Maxwell's House is brought to you by Cachefly at CACHEFLY.com. This is Maxwell's House with Ray Maxwell, episode 50, Lasers. It's time for Maxwell's House, the show that covers whatever Ray Maxwell's darn well interested in. And boy, that could be a lot. Ray is a raconteur, a teacher, a color scientist, a pilot, a photographer, a Photoshop wizard. Have I left anything out, Ray Maxwell?
That'll do for now.
Quite a bit, no doubt. He's also a polymath who's interested, if you can look the word up, it's exactly what he is. He's interested in everything and has taught himself everything there is to know about every subject in the world. And so it's always fun to find out what's on Ray's mind. And that's all this show is what's on Ray's mind this week.
Well, our main topic for this show is going to be lasers and the history of the first laser.
I love lasers.
But I do have a few odds and ends that I usually have that I start off the show. I've got one sad note. A very good friend of mine who was a aerospace pioneer in Canada, Dave Sloan, passed away this last week. It's been a rough year for me with friends, as you know.
No kidding.
And Dave, unfortunately, had a brain tumor that he's suffered with for 16 years. So this was not unexpected, and he's been in full-time care for the last 5 or 6. But he was a pioneer in the remote sensing community and was a pioneer at McDonnell Detweiler and doing the first Landsat ground stations for a number of countries throughout the world. And he was the impetus to go into that business and got MDA into the remote sensing business when it was a small handful of 10 or 12 people. And the company's now, I don't know, 1,000 people or something. It's been even larger than that.
Wow.
So, and now they're doing synthetic aperture radar. They're doing... they're actually doing the satellites, the radar sat and so forth that go up. So he was a pioneer in that area, and we're sorry to see him go. And tonight we're going to gather at a friend's house and celebrate his life. So
wonderful. That's a wonderful thing to do.
Right. And then this is on a totally different topic. Several people have asked me, and I heard you mention it on one of the other shows, is it possible to burn HD video to a standard DVD?
That's a really good question.
And it turns out that it is. Toast 10, if you buy the Blu-ray plug-in, has a mode where it can record an HD movie to a standard single-sided or double-sided DVD. But the caveat here is it will only play back in a Blu-ray DVD player that will also play DVDs.
Okay, so the Blu-ray DVD player has to support the DVD format, but then, having done that, it will play it back in, is it 1080p?
Yes.
Interesting.
Now, there's another caveat here.
Yeah, there's plenty, I'm sure.
The other caveat is the latest. I tested this with the latest edition of Toast 10 and couldn't get it to work, and went on the internet and researched it, and everyone is saying that it works in 10.0.2.
No.
But after they added a few more features, I have a feeling they didn't do a good job of regression testing, and it's broken in the latest version.
That's too bad.
But it is possible, and I did it earlier. But with the latest version, when I went to test it again, but before I said anything about it on the show, I found these hiccups. And by the way, that brings up another interesting topic, and that's the topic of regression testing. Are you familiar with that term?
I've heard it before, but I tell you, if you asked me to define it, I wouldn't be able to. So what is regression testing?
Regression testing is any time you change anything in a system, you have a written test that tests the basic overall functionality of the system. For instance, now, and I did this in the best spirit, and I hope Colleen took it in that. The other day, you came on, and there was a cable disconnected.
I know that day, yes.
And so I wrote her a private note and said, let me introduce you to the term regression testing. And what you do, and I sent her a copy of one of my checklists that I use before I go on air every week. And to check that I've got everything set up and ready to broadcast. And I said, you could write down a set of tests that just test the overall functionality of each of the things you intend to use on that thing. And you just, anytime you work on the system at all, and it can be, you think it's, oh no, I just worked on this one little part. Yeah, but you don't know what effect it has on other parts.
Right.
And so you run this little checklist, just like a pilot runs a checklist before he takes off. And regression testing, where I really came into familiarity with it, was when we were doing computerized airline flight dispatch systems, where we're dispatching aircraft. Yeah, where we're flight planning and putting the correct amount of fuel on the plane and so forth.
A mistake there would be pretty bad.
Yes.
One of the things that's interesting is that in modern software development technologies, they're trying to avoid this problem as a class of problems. It comes because things are interrelated, interconnected.
Yes.
So a change in one thing affects other things. And that's the whole idea of object-oriented design, is that every bit of functionality is a black box. Mm-hmm. So you can modify it as long as the inputs and the outputs are not modified. Any modification you have here will really reduce the impact on the system as a whole. I wonder, that makes sense in software. I wonder if that could also be done in hardware or in real life engineering.
Mm-hmm, mm-hmm. Oh, I think so.
Reduce dependencies, I guess.
Right, reduce dependencies. But even in object-oriented software, occasionally,
it happens. Absolutely.
You can get a surprise. You say, well, this won't affect that, but there's a sneak path or something you haven't thought of. As the complexity of the software increases and increases and increases, you often have, interrelations that you're not at the top of your consciousness and that have slipped into the way you're coding the thing.
Yes. Yeah.
Now, I just mentioned airlines. This past week, I had a thought for an idea. Every time I fly nowadays, I have to, I am a fan of aviation. I'm a pilot. But I dread flying anymore because of all the security, and I have to go 2 hours ahead, and I have to be treated like a criminal, and I have to be shaken down and take off my shoes. And I don't know, the whole thing is a very, I have to just tune out because if I think about what's going on, it gets under my skin. And so I take my iPhone or iPod and listen to a podcast or something. But, I try and just have something that occupies my mind without thinking what I'm being put up with.
It's one of the secrets to the success of the podcast industry, my friend. Right. There's a lot of times when I wish I could zone out.
Precisely. Yeah. And but I've come up with a thought. The whole object of this security and everything is the fact that they do not want a terrorist to get in charge of an aircraft, to get in command of an aircraft. And I've also explained with some of the fly-by-wire aircraft, and even those that aren't full fly-by-wire, that they can actually land under the flight management computer control completely. So here's my thought. What if you had a super secure, super encrypted communications link with the plane? Now, notice I said with the plane. I didn't say with the pilots. I said with the plane. And basically, before the plane leaves, you load the flight path that aircraft should follow. And if that aircraft tries to deviate from that flight path without an encrypted signal from the ground allowing it to deviate, because sometimes they have to, of course, the aircraft wouldn't let you do it.
Just eliminate hijacking and
Yeah,
completely.
That airplane would fly the path it's supposed to and land.
Well, you know who wouldn't be happy about that?
Well, of course.
The pilots.
Yeah.
There's no overflying Minneapolis anymore.
That's right. Minneapolis wouldn't have happened.
You got to go there.
The guys would have woken up and say, "Wait a minute, what's this plane doing? Oh, it's just
landing us.
It's descending and preparing. Oh, we're over Minneapolis, you know." And the truth of the matter is, they might still have their pilot's licenses today.
True. Good point. Maybe
But all I'm saying is, from a technological point of view, that now is a possibility.
Yep.
You know, it is possible that you could put together a system that now that doesn't mean that with the proper command from the ground, from air traffic control, that you can't deviate or deal with, you know, a situation. And you know, you could have essentially a request to deviate that, you know, could be initiated by a single button or something, and the guys on the ground could say, "Okay, I'll let you deviate until you explain why," or whatever. You know,
you'd have to build something like that in.
There'd have to be heavy redundancy, heavy encryption, a lot of triple security.
The pilots would never let you do it otherwise.
No. And the other thing, just before we dive into the big, deep topics here, after last week's show where I did that heavy-duty show on forensics, I got a few fan mails, and I got one from Swiss Compass that I really appreciated. He said, "I think you need to add some levity to the show." So he sent me a link for a YouTube broadcast of Brian Mallow, the science comedian. Have you seen him?
I have. Yeah. In fact, I think we're trying to get him on Dr. Kiki's show.
Oh, do. Because now I'm with full credit, I'm going to borrow just a few of his jokes to add levity to the show today. But they're Brian's. You know, I didn't think these up. He was giving a talk on viruses, and he said a virus walks into a bar. The bartender says, "I'm sorry, but we don't serve viruses here." The virus invaded him and said, "Now we do."
Okay, that's a bad joke.
All of these are bad.
It made me laugh, but it's a bad joke.
An infectious disease walks into a bar.
Yeah.
He says, "I'm sorry, we don't serve infectious diseases here." And the bacteria says, "You're not a good host."
That's good. That's good.
Now this is my favorite here.
Okay.
Sorry, that was the infectious disease. 2 bacteria walk into a bar, and the bartender says, "I'm sorry, we don't serve bacteria here." And the 2 bacteria say, "But we work here. We're staff."
With a PH. Very good.
All right, enough. Ray has had, you know, with the other guy's material.
Science comedy, ladies and gentlemen. It must be in the delivery, to be honest.
Yes. And that's what I said. The real secret to comedians is their timing and delivery.
It's all about
and their interaction with the live audience.
Although, if you have an instant rim shot, sometimes that helps.
That's right.
Sorry, I was a little late on that.
Yes. One more
instant rim shot? Tell us a joke and I'll have it.
Okay. Schrodinger's cat walks into a bar.
Yes.
Or didn't.
Wah, 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 wah. That's pretty abstruse. Okay.
Yeah. As he told these jokes, he kept saying, "This is going to be understood by a narrower and narrower part of the audience." You know?
He's on Twitter, by the way, Science Comedian on Twitter, and I'm pretty sure he's on an upcoming show of Dr. Kiki's Science Hour.
Good.
So I'll make sure that I let you know what day that is. Maybe you can stick around and
I'd love to.
Yeah.
Right. I certainly enjoyed his. He's all over YouTube. Just look up his name on YouTube, and he's got lots of different stories and jokes.
Oh, yeah. And he's also at sciencecomedian.com/blog.
There we go.
He must be a scientist.
He's definitely got a science background because the jokes are very inside jokes for scientists. Yeah. But he also does other straight stand-up comedy. And
if you could call it that.
Yeah. Anyway, so thanks to Swiss Compass, you know, we came through with a little science humor today.
Science humor.
So that brings us to our key topic, which is lasers. Now, Let me preface this with, I was extremely privileged when I worked at Creo. The chief technology officer was Dan Gilbert. And, by the way, I do want you to hook up to GoToMeeting.
All right.
Yeah.
I'm going to run over there right now and get it set up for you.
And I am showing my screen. While working at Creo, Dan Gilbert, the chief technology officer, and I've spoken of him many times, he's one of the most brilliant technical guys, found out that the original inventor of the laser, who is Dr. Theodore Maiman, Ted Maiman, moved to Vancouver after he retired, he and his wife, and they lived here in Vancouver until he passed away in 2007. And his wife is still here in Vancouver, and Dan knows her. But Dan found out that he was publishing a book about the first laser called The Laser Odyssey, and here is a copy of it. This is the story of inventing the first laser.
Wow.
And Creo actually helped with the cost of publishing it because Creo, all of their main products were dependent on the invention of the laser and further additions to the laser that Dan Gilbert did. So he ended up befriending Ted Maiman and invited Ted to come to Creo one day for what we had Creo University on Wednesdays at lunchtime, and we had various guest speakers, and I spoke at a couple of them on color science. But on this occasion, Ted Maiman came to Creo, told us the story of inventing the first laser, and brought the first laser to Creo, powered it up, and fired it for us. It was a pulse laser. So I actually got to meet the man that invented the first laser and got to touch the first laser.
Wow, that's really cool.
And his wife still has that original laser.
That's really cool.
Yeah, yeah. So that's why this topic is very special to me. But
do you want to define what a laser is?
That's the thing. Oh, beautiful transition. Right in my notes. Laser.
What is it?
Yeah.
Wait a minute. Let me see if I can remember. It's something about, well, I know it's coherent light, but it's LASER. Excited, emitted. I don't know.
It's light amplification.
Amplification.
By stimulated emission of radiation.
I knew that.
Yeah.
Lasers.
Now, it was the forerunner to it was the maser, which was microwave amplification by stimulated emission of radiation.
Interesting.
Yeah. So, first of all, what does it output? It outputs coherent light. Now, just so you understand, a radio transmitter emits coherent radio waves. CW transmitter, that's when you're sending code, it sends out an absolute single frequency. Without modulation, the carrier wave is a coherent set of photons. Radio waves are electromagnetic radiation. It's the same kind of thing as light. It's just at a different frequency. And our eyes happen to be sensitive to this one narrow region we call light. But radio waves and light are both electromagnetic radiation, and so are X-rays and gamma rays and infrared and ultraviolet and so forth. All of those things are electromagnetic radiation. So in the early days, at low frequencies, we were able to build devices using tubes and so forth that would emit a coherent signal via antenna to produce radio waves, where all of the waves were in phase, and with the proper antenna systems, we could direct them and focus them in a very precise direction if we chose. And that continued to, we continued to learn how to build coherent radiation up through microwave. And the maser was the device that could amplify or produce microwave signals that were coherent at one narrow frequency. Now, light is 10,000 times higher frequency than microwave. So Maimann's task, or the task for someone inventing a laser, was to increase the capabilities of the equipment to produce a coherent electromagnetic wave 10,000 times higher than anybody had done it before. So let's talk a little bit about, let's go back a little bit of the history. And it requires that you excite atoms with some form of energy, and it can take several different forms. It can be light, photons, it can be heat, photons, it can be electricity. You can use any of those things to excite atoms. So when you excite an atom, if you'll recall our earlier programs where we described the atomic structure, there are electrons with various energy levels or orbits. And if we excite an atom, we can move an electron from one orbit up to a higher energy level. And from quantum physics, we learned that there's a discrete amount of movement or energy. It goes in steps. And that's what quantum physics is all about. So if we excite an atom from its ground state, I'm going to introduce some terms as we go along here, to its excited state. And by the way, another bit of science humor, one of the people on the IRC chat today, I announced ahead of time that I was going to be talking about lasers, and one of the guys came back and said, "Oh, I'm excited." Because you have to excite the atoms from their ground level.
Oh, another comic.
Another comic.
Another joke.
We have them in the IRC chat.
Yes.
Okay.
I'm so excited.
He said, that's all he said. I'm excited.
But barely coherent, so there you go.
Right. So, at any rate, we can excite an electron to move into that next state. Now, if that's all we do, the atom in its excited state is unstable. And the electron will fall back to its ground state. But when it does, it has to do something with that energy that was put in. So it absorbs energy from being excited. And when it falls back to ground level, it emits a photon. However, when it emits a photon in that condition, it emits it at an approximate frequency. It's a band of frequencies. It isn't a single frequency, and it emits it in any direction. It's a random direction, and it varies in frequency. And an example of that is if you look in your toaster, and you see those red wires, those tungsten wires that are those atoms in the tungsten are being excited by the passage of current through the tungsten. And then as the atoms go from their excited state back to ground state, they emit red photons and heat. But that is over a band of frequencies and in all directions. Same thing in a light bulb. Same thing in a fluorescent tube. Only in a fluorescent tube, we have a mercury vapor that emits ultraviolet when the atoms fall back, and then the ultraviolet stimulates the phosphors on the outside of the tube to emit light in the visible spectrum. So all of those are examples of excited atoms emitting photons, but it's incoherent, and it is called spontaneous emission. Later, I'm going to introduce another term called stimulated emission, and it's going to be coherent light. But so in a standard light bulb, standard toaster, if we run current or stimulate the atoms, they get excited, they go up to this higher energy level, and then when they fall back randomly, they emit random frequencies in random directions, and we call that, in the case of the light bulb, white light. They emit energy over a wide spectrum of the visible spectrum. So that's a standard light bulb and spontaneous, incoherent radiation. However, Einstein and some of the early physicists predicted that if you got a group of atoms into an excited state, into that higher energy level, and you could get the majority of atoms in a substance, be it a gas or a ruby or whatever. There were a lot of candidates. If you got it into that higher level, and then you introduce another photon that happens to be, and notice that I said happens to be, at exactly the right energy level, the atom this time will emit a photon that's in phase with the incoming photon. It'll be in phase at the exact same frequency, and it'll go out of the atom in the same direction as the photon passing through it. So now you put one photon in, and two photons come out. That's amplification. So one of the photons is being sent in by the pumping energy source, and that's what it's called, pumping. And the second photon is emitted from this excited atom when it collapses back to the ground state. But the two photons that come out now are in exact phase, the same frequency, and traveling in the same exact direction. And that's lasing. Any questions, Leo?
No, that makes sense. It's amplification. Oh, it always works that way, doesn't it? By reinforcing?
Yeah. Now, if you, do you have the, you've got, okay.
I do. I'm ready to see your screen.
All righty. I'm going to bring up my screen here and get to my correct slide. So in the first slide here, let me stop it here. I just want to show that Maimon chose to use a ruby, and there's a bunch of history that I'm going to get to here very shortly. But this is a piece of ruby. And this lightning bolt shows he used a flash tube to stimulate or to put radiation into this ruby crystal. Now, when he could get these atoms stimulated to this higher level, and by the way, when you do that, when you get most of the atoms in here into the excited state, and you have more in the excited state than you do in the ground state, that's called an inverse population. You have more atoms that are stimulated than those in the ground state. When that happens, and a photon comes into this ruby, if some of them happen to align and start traveling down this ruby, and they start hitting other atoms that are already stimulated, you get a multiplication. So the first one photon goes in, two comes out. If they hit another pair of atoms, then two go in and four go out, etc. So it multiplies exponentially. Remember last week? And it goes down till it hits this mirror at one end, and then it is reflected and goes back and makes another pass through this ruby until it hits a mirror at the other end. Now, you can use a partially silvered mirror at one end and let some of the energy come out, and that's where the laser beam comes out. Now, in Maimon's case, in that very first laser, he actually used fully silvered mirrors on both ends and then took a pin and just scratched a little hole in the end down here, and that let the laser light come out. And, of course, the light that's coming out is all at the same frequency. It's coherent light, and it's very, very tightly focused. The beam is very parallel. And very shortly after he invented it, they were able to send a pulse of light all the way to the moon. I don't know whether you remember.
I do remember that. Was that the goal? Was that why they were working on this?
This is one of the goals. Now, it turns out there's so many applications for lasers today. I mean, we've got them, laser printers, we've got DVDs, CD players, the blue laser in Blu-ray player. Lasers are all over the place. Plus, so there's laser altimeters and laser cutters, and a friend of mine sent me an article about a group in Seattle that's just won a $900,000 prize by taking a laser and driving a object up into the sky 900 meters at greater than 2 meters per second. Now, what they're working on there is they're talking about having a way to reach space using lasers, and the power source stays on the ground, so you don't have to carry all your fuel. And with a laser beam that stays tightly focused all the way to the moon and back, it is possible to drive an object from the Earth up through the atmosphere without that object having to carry fuel. That's a very exotic use of the laser today. Now, let me carry on here a little bit. So now we have an understanding of what a laser is and how it works. And let me just go to the next slide here and show you. This is a cross-section of Maimann's actual laser, his actual first laser, and he used a flash tube, this spiral flash tube around the ruby. And then there was a power supply, and there was, to get a flash tube to fire, this is a trigger element that puts a sudden high current into the vicinity of the tube and causes it to discharge. And then it emits photons in a fairly wide band. A xenon flash tube emits a lot of energy in the green and blue end of the spectrum, and it turns out that that is the absorption frequency of a ruby laser. A ruby laser looks red because it absorbs green and blue light, and it actually fluoresces. At low energy levels, it will fluoresce in the red region. But that's why rubies look red, is they absorb blue and green light. So he chose a light source that was very rich in in green and blue light. So let me go back and give you a little bit of his history and how he came to be this first inventor, because I think it's fascinating. He studied with Willis Lamb at Stanford and received his PhD from Stanford in early 50s. I think it was 51, if I'm not mistaken. And then I want to give another piece of history, because all this will come together. In 1954, Charles H. Townes, Townes, his group produced a maser, which was a microwave device that emitted coherent electromagnetic radiation in the microwave region of the spectrum. In 1954, Townes and another scientist, Arthur L. Shallow, wrote a paper saying that it's possible to use similar techniques, they thought, at optical frequencies. And later, they were given a Nobel Prize for their paper possibly predicting in the future the possibility of creating a laser. However, Townes and Shallow did not make a working laser. Now, in fact, in 1958, and this comes out fairly clearly in Ted Maimann's book, The Laser Odyssey. In 1958, Shallow delivers a paper at a conference, and I can't pronounce this, but it's Shah and Ga Lodge meeting in 1958. He produced a paper in which he said that a pink ruby was a poor choice for lasing. Huh. Now, just so you know, there's such a thing as a pink ruby. And let me just explain what a ruby is. A ruby is just aluminum oxide. An aluminum oxide is crystal clear. It's a sapphire, all right? But if you dope it, and this happens in nature, with chromium, a very small chromium, then it turns red. It absorbs energy in this green and blue region. And the pink laser is doped, or they add 0.05% chromium to create a what they call a pink ruby laser. The dark ruby laser has 0.5%, 0.5%. So, and Shallow believed that the dark ruby laser was the way to go because it had yet another energy state. In Maimann's invention, he uses the three energy levels of the atom: the ground state, the excited state, and then this emitting state where it emits the other photon. The dark ruby has a fourth level that's between the ground state and the emitted state, and I'm not going to go off and explain why. Later, they did make four-level materials lays, but Shallow and Townes thought that was the only way to go and that the three levels would not work. And that was one of the insights that Maimann had. Maimann didn't listen to the gurus. The other thing you need to know...
Always a good idea.
Yeah, that's right. Another thing you need to know is Bell Labs and TRW and some other universities were spending millions trying to develop a laser, and none of them has succeeded up to 1960. All right? Now, Maiman went to work for Hughes, and one of his first jobs was to build for a government contract a maser. Now, this is a microwave device. This has nothing to do with a laser yet. This is at a much lower frequency, microwave frequencies. And there was an existing design that Towns and Shallow and other people had participated in that involved using a 5,000-pound magnet, using what's called a double dewar. A dewar is a vacuum bottle, essentially, that lets you do cryogenics or lets you cool things down to super low temperatures. And they had an outside dewar that had liquid nitrogen in it and an inside dewar in this vacuum bottle that had liquid helium. Now, liquid helium, I believe it goes down to 4 degrees Celsius or Kelvin above absolute zero. So to make this maser work, you had to really get things cold. And of course, keeping it cold is very difficult. You have to have very good insulation, and they had to have this 2-layer thing to achieve these low temperatures. And then they had a ruby glued on inside a cavity, a resonant cavity, that was the right length for the microwave. And that was their original design for the maser. Now, I want to give credit where credit's due. A maser was used along at Bell Labs with a large antenna that discovered background radiation of the universe and the signs of the Big Bang. So the maser did do something in history, very interesting, very important in physics. However, you have to understand that how many masers do you have in your studio today, Leo? And how many lasers do you have in your studio? Whoops. Oh, I've lost you.
I turned off the mic. Sorry. I forgot that.
Your lips were moving.
I was saying, unless I'm greatly mistaken, I don't believe there are any masers. However, of lasers, I know that each computer has a CD player. That's at least 10.
Right.
And there must be other lasers in here as well.
Laser printer? Do you have one of those?
There's a laser printer.
Right.
How does that use a laser? I always wondered.
Oh boy, another show.
That's another topic for another day.
I can explain it, but
I know you can.
They have a charged drum, and the laser, when it writes on it, takes
drawing.
the charge away. Got it. And where there's still charge, the toner collects on it and prints on the paper.
Right.
Yeah.
So there's another one out there.
Oh yeah.
I suppose there's others in other places. I don't even think.
Right, and there's cutting lasers, and
we had one. Jerry Ellsworth brought one, and I etched the back of my Droid phone. Actually, that was
fun. So what I'm saying is lasers are all over the place now
for surgery,
and but at any rate, Maiman was asked to design this maser for a government contract when he first got to Hughes. And I gave you this 5,000-pound magnet, double dewar, and all that. And they said, well, just build another working unit like that. And he said, no, I'm going to take a crack at engineering this and making it much smaller. Well, I won't put you through all of the details, but he produced a laser that the entire laser and power supply weighed 25 pounds. And he did this by filling the cavity with ruby to increase the dielectric effect. And all I'm saying is he produced a maser that was much better than the original maser. And the government was very happy. It had a higher gain bandwidth. It had, it performed better. So then...
I want to thank Web0447 in our chat room for pointing out that our fiber optic cables for our SAN, of course, use a laser to send the data down the glass tube.
And all of those lit fiber optics sending the signal, all of the internet, it's all lasers.
Lasers.
So at any rate, Maiman chose against all odds and against all the gurus who were telling him not to, he chose a pink ruby. And he modeled in mathematics how he thought this atom would perform. What I'm saying is he was very theoretical. This was not an accident. He didn't go in and just accidentally stumble on this in the lab. He predicted this from first principles of physics, but he thought about it in a different way. So he found he felt that the pink ruby was very stable and rugged. It had these broad pumping bands. In other words, it absorbed energy across both the blue and green spectrum and UV somewhat. And one real key thing is the pink ruby laser works at room temperature, no cryogenics. So he didn't need all of this complicated Dewar stuff. So, these were incredible insights. They were all against the grain. So on May 16th, 1960, this laser that I have up on the other computer, designed exactly as you see it, with the flash tube around the ruby crystal, it looks fairly simple, was born. And he was able to fire this thing up, and when he got to a certain energy level on the power supply, suddenly the energy coming out that he was measuring with a sensor started to spike. And then later, this is a little side story, he borrowed a spectrophotometer, a very high-quality one from another project in Hughes, over the objections of the other scientist who didn't want to give up his instrument. He got a hold of this and showed that when the thing starts lasing, the frequency of the energy coming out gets extremely narrow. In other words, as you stimulate at low energy, it fluoresces, and you get a low amount of energy out over a broad red spectrum. But as it starts to laze, it goes to a single frequency. And so that was his proof that it was coherent light. And, some of the other scientists, when they finally announced this, said, oh, it's an artifact, or he doesn't know what he's doing. I mean, because you've got to remember something. The other people working on this were big, multi-million-dollar labs. Bell and TRW each has spent over $2 million on this project. Mayman he did this over 9 months, and he spent a total of $50,000, including the salaries of the people who worked on it with him. And,
wow.
So they were reluctant to give him credit for this because he was not an academic. He had gotten a PhD and not joined a university. He had gone into industry. He was had sold himself to the devil in some academics' point of view. And he had gone against all of the advice of all the other people and many of the papers that were written at the time. So he went on to leave Hughes, and he managed to do a deal with Hughes, because Hughes, after they were all excited, they did a news release, and they did it prematurely that prevented him from getting any foreign patents on the laser.
Oh, no.
Yes. So he did get a patent in the U.S., but you'd have to go into the patent law at that time. But their premature announcement of it through the wrong channels. He also wrote a paper and submitted it to Physical Review, which was the most prestigious paper, and they said, oh, we've got too many papers on masers, because to them, lasers is all the same, and they refused to publish his paper. He finally was published in Nature, another scientific review, and the truth of the matter is he never made a great deal of money. He went on to form his own company, build high-powered pulse lasers in industry, and did okay. But there were many people that were reluctant to give him credit because all I'm saying, let me shorten it. There's politics and human sociology, even in the scientific community. According to his book, he suffered for it.
Well, and of course, any invention, I mean, just, look at Edison, look at Tesla. Look at, any invention, especially one of value.
Right.
People go crazy about. That's not. A lot of times they use the word laser, probably inaccurately, like a mouse, an optical mouse. That's not a laser. They might call it a laser, but that's not a laser, is it?
I believe it's an LED.
Yeah, I think it's just an LED.
Yeah, there's a light-emitting diode that puts out a broadband red beam.
It's not coherent though.
And there are semiconductor lasers. Like
laser pointers. Are those?
Laser, yeah. If I
how coherent are they? That's a. Ow! Stop it!
Now that is
that's a real laser.
That's a semiconductor laser pointer. All right, but that's not an LED. That's and by the way, you have to watch you don't use the term solid state laser because the first Ruby laser was a solid state laser, but it was not a semiconductor laser. That was fabricated on silicon.
Right.
And by the way, they work on the same basic principle, except this laser is pumped rather than with a flash tube or light. It's pumped with a couple of batteries, electricity. And you again excite in the substrate of this semiconductor. You excite atoms to that, get an inverse population, and then you have a small cavity in there of material, dielectric material in this case, and you get this same lining up of the photons, and they get in phase, and away you go. Now here's another little footnote to this that I think is interesting. Again, I study quite a bit about color science and human reaction to these various kinds of radiation, because that's what color science is all about, is the fact that color happens in our brain. I can't demonstrate this by shooting this into the camera, but if you've played with a laser pointer, you know that if you look at the red laser beam that comes out of it, reflected on a piece of paper or whatever, it looks grainy. Have you noticed that?
Yeah, absolutely.
Yeah, it looks grainy. That graininess is happening at your retina. The beam is not grainy.
So
that's a human response.
Wow.
Yeah, that's an image that is created on your retina, but it's not. The beam really doesn't look like that. That's something happening on your retina that causes that grainy look. Well,
our friend Steve Wozniak is a big laser pointer guy.
Mm-hmm.
And we had so much fun. He was on a Mac Mania cruise with us, and he has some illegal in the U.S., I think, high-powered. He has a green laser,
yes,
which is, I'm sure it should be illegal. It's very powerful. And he would do things like shine them into a glass of water, and it was incredible the things you can do with these things. They're beautiful. And yellow, green, red, of course, is the easiest to find and easiest to get.
Right.
Apparently, the yellow and greens are rare, and blue. I believe he had blue as well.
Yes, those are very rare.
Yeah. But
now the blue has gotten a lot more common with Blu-ray, but early on it was very difficult to make a blue laser.
Well, he would shine it. He'd say, "Anybody have a diamond ring?" He'd shine it to a diamond, and it would just fill the room with light. It was amazing. Mm-hmm. Because there's so much power going into that and refracted out. It's like a disco ball. It was really fun. But you're right, exactly. You see that kind of sparkling little graininess, and it looks like it's grainy.
Right. Now, let me tell you a misuse of lasers. I was out flying just this last week. In fact, Tuesday night, and I took off from Vancouver. I was flying my friend's pressurized Cessna 210, and we were just going out for some night approaches and circuits out at Abbotsford. And as we left took off from Vancouver International, tower operator said, please take note, out in the area you're flying into, we've had reports of someone with a green laser, attempting to blind pilots,
Isn't that awful? Who would do such a stupid thing?
I don't know. That's sick. We didn't see any, by the way, but pilots have, and there's they've shot it in airliners. People, 300 people on board, and they're playing with a laser trying to
kids,
blind.
But they're just annoying.
Yeah,
they're just so annoying, and they don't get what they're up to.
No, it's absurd.
It's got to be a kid. I can't imagine anybody else would do that.
Right. That'd be pretty sick.
Yes. Yes.
But
I have a news story I just want to run by you.
sure.
Did you see that the LHC is down again? Maybe the future is trying to tell us something.
Well,
Did we talk about that on this show? Was it on this show that we talked about
Yeah,
that?
I think we touched on it, and I think we touched on it.
Here comes Kiki. Kiki might have something to say about the LHC being down again.
Is it down again?
It's down again. The future has spoken. We are never going to see a Higgs boson. So for those who don't know what we're talking about, two very prominent scientists, one of whom was the founder of string theory.
But it did go up above what the Fermilab's amount of...
Sit down and get on mic if you're going to say something, because we don't hear you. But these two scientists posited that maybe the reason this baguette dropped by a bird broke the LHC, maybe the reason for all these problems with the LHC is because in some weird Schrodinger's cat kind of way, the Higgs boson did not want to be discovered. And so they said, well, there's an easy way to prove it. If it never reaches energy sufficient to generate a Higgs boson, but you're saying, Kiki's saying it did. Then you can't, these guys are smart scientists.
No,
Pull up a microphone.
I'm gonna get the mic.
Get the dog out of the chair.
Leo, vis-a-vis last week's program, are we suggesting that the Higgs boson might have sociopathic tendencies?
It cracks me up that a legitimate physicist would even propose this.
Oh, it just shows his creativity. That's all.
I think it's fascinating.
Think outside the box. Come up with some new ideas.
Right.
People can go, it's a silly idea, which I think it's an absolutely silly idea. I mean, the reason that a baguette blew the breaker of the LHC is because somebody didn't plan for baguette breaking. I mean, you had all the things you have to plan for in designing a giant instrument like the LHC, baguettes. I mean, when is that on your possible problems
But the fact that it even had a vulnerability in that regard is pretty amazing. Well, now the latest one.
Yeah, vulnerability, baguettes.
Let me see if I can find the new problem. Knocked out by another power failure. This was yesterday.
Power going through it. I'm not surprised.
Knocking not only the Atom Smasher itself out, but even its associated websites were put offline. I'm telling you, the future is responding.
What this all begs, though, is there are physicists who point out to us that when you sit down and look at all the equations for quantum physics and all this sort of thing, there's no positive proof that there's an arrow of time.
Right.
Time is something we perceive, but that it should be, from the laws of physics, reversible. So that's where they get all of this. And that's, but I'm not quite ready to buy into that one.
Boop, dilly, bloop, bloop, blah, bleep. That's what the physicist said.
Maybe there's some paradox that would be created by this event, and it's just
right.
Nature abhors a paradox and just won't let it happen.
Yeah, people that we need to get on the show to discuss this: Brian Cox, who actually is part of the CERN team working on the LHC.
Right.
Sean Carroll, who writes a lot about the arrow of time and things of this nature. He'd be a great person to talk to as well about the truth in the conjecture.
Well, let's wrap up. I just wanted to mention that. And Kiki's here, as you can see.
Right.
And feisty.
Hi, Kiki.
I'm feisty. I'm
Did you
drinking
eat?
coffee. I had a couple of bites of sandwich.
Go finish your sandwich.
I'm ready to go.
She shared her sandwich with me because my Nutrisystem diet was supposed to come today, and it didn't. And I don't have any lunch, and so it was very kind of her to feed me.
I fed Leo.
You feed me.
Yes. It's like feeding a baby bird.
No, it's not. No, it's definitely not. Maybe a hungry alligator.
Yeah. I just made sure to pull my hand back really fast.
So, anything else to say on the subject, Ray, before we wrap her up here?
What I'm going to try and do is a follow-up, and this is a try. I can't promise this yet, but there's a group in Seattle who has used lasers to send an object vertically. I mentioned this earlier. And the fellow who does that is an acquaintance of one of my close friends. And I'm going to find out if this guy in Seattle has Skype. And I'd love to talk to him about the possibility of launching spacecraft using lasers. Again, the whole objective. And by the way, he just won. He exceeded 2 meters per second. The next level of the prize is at 5 meters per second. And they got 4-point-something meters per second on this trial. And they won a $900,000 prize. So, and the next prize is $1.1 million. Okay.
And what are they measuring the speed of?
Okay, an object. Now, okay, here's what they did. They have a helicopter hovering at about 3,600 feet with a cable. So the cable is just to guide this object, all right, because there's other considerations. But then there's this object attached to the cable, and they have a laser on the ground that's driving this object up the cable. And they were able to get it to climb to 900 meters in 4 minutes and, I forget, just over 5 minutes, which works out to be below 5 meters per second, but greater than 2 meters a second. And there was a prize for 2 meters per second. And of course, what they want to do is keep driving this up till they get to escape velocity or whatever to launch things into orbit. But the key thing with this laser lifting system is that the energy source is on the ground. So the object going up in space does not have to carry fuel.
Carry this weight. Wow.
Yeah.
So this is a laser rocket launching capability.
That's right.
Wow. That's pretty cool.
Right. And they're doing
I love science. I love scientists. I love engineers. I just love the ingenuity. Wow.
So if I can get in touch with this guy, I'm going to see if he'll come on as a guest.
Is there?
Because I'm sure you'd have 1 or 2 questions for him.
Yeah, I mean, so there's enough impulse power in the energy of this light beam to push. And how heavy is this object it's pushing up?
The object is pushing up is fairly light right now.
Right.
But it's a proof of concept, and then if it's scalable,
that's neat.
There you go.
Love lasers.
Yeah.
Thank you, Ray Maxwell. You can write to Ray. He's ray@twit.tv.
Yes, pass along any ideas you have for a show or questions or what have you. I enjoy getting your fan mail.
Wow. That's great. Thank you, Ray. We'll talk to you next week on Maxwell's House. Congratulations on episode 50, by the way.
Okay.
Wow.